Okay, we got 82 people, including the presenters on. That's leveled off. We had a few, as is always the case, technical issues that I think we've got ironed out well enough to proceed. Welcome to today's webinar on digital stringless milling. Every time I think of this project, I think of one of my favorite quotes from a movie.
Months to clear up the red tape. You know, I have one simple request, and that is to have sharks with frickin' laser beams attached to their heads. Now, evidently, my cycloptic colleague informs me that that can't be done. Can you remind me what I pay you people for? Honestly, throw me a bone here. What do we have?
So when I started, if somebody would have said, we're going to have construction projects with frickin' laser beams attached, I would have said they're crazy. But as times have changed, and here, I guess today I'm the Dr. Evil, and this is my assistant. We have 3 people who are not evil henchmen, but very well regarded and knowledgeable people on this particular topic. We're going to learn about how we used frickin' laser beams to do highway construction. We're going to start out with Kyle Klasen with WSB. He knows all the magic behind the building of the models and what a model is. I think when someone tells me a model, I'm thinking of gluing together a plastic airplane or something. So this is, again, high-tech stuff. We have Tom Abell from SciTech, who is sort of the equipment expert in terms of what we need and how it's going to work. And then we got Dan Schellhammer, who's got to take all this and make it work out in the fields. And Dan is from Midstate's Reclaiming. So I'm going to let Kyle take it away.
All right, thanks, Curt. Yeah, my name is Kyle Klasen. Little background, I worked for MnDOT from about 1988 to 2006 in District 3 in St. Cloud. I was there as a highway inspector, survey crew laborer, through a crew chief, office man, and eventually in RLS there. 2006, I came to WSB, and now I'm currently the director of surveys. And through my time at WSB, I've really got to know a lot of contractors, and I've really been engaged with generating files for contractors used for automated grading, stringless milling, concrete paving. So what I'm hoping to do today is just talk a little bit about the backside of what we do to prep files for contractors, some of the stuff we need, and a broad overview specifically for stringless milling projects, some of the efforts on the engineering side to get surfaces out. So I'm the one that's having the technical difficulties, so I have someone else running my slideshow. So if we could go to the next slide, please. There we go. So here's what I'm going to try to cover today. I'm going to run through basically control for the project, the existing data that we use for design, and actually some of our practices in design to generate these surface models. So first we're going to talk about the control. Can you go to the next slide, please? Okay. The first thing that we do is obviously we have a plan set or a project. It's designed in certain controls. So our first thing we do as our foundation for everything that's happening on a project is tie into MnDOT's geodetic control. This is a snippet right from OLM's website in their geodetic viewer. So we pull all the data out of here, and you can see the different control points throughout this project, the names, approximately every mile or so. So if you can go to the next slide, I actually pulled the data sheet. One of the control points is called MAT. So if you go to the next slide. So this is what we get. They're about every mile on the project. This particular the actual, what you just seen was actually Highway 23 south of Granite Falls, and that's an active project right now that I am working with Midstate and a few other contractors on a specified stringless milling project. So you can see here, it gives the coordinates, elevation. So we first build our geodetic control network up on this project, and then from there, we move forward and set all of our project control. Go to the next slide, please. Can you go to the next slide, Tom?
Yeah, it's switched, Kyle. It must be just a little delay on your end.
Oh, okay, no problem. So everybody else there, you got to bear with us. We were having some technical difficulties with me being able to present this slideshow. So here's another clip now again. This is on the 23 project, the actual project going on right now in District 8 with the specified stringless milling. And you can see here now, we set project control now that's based off of our geodetic control every 250 feet. We alternate the monuments on each side of the road, and we use in 3-minute control point observation on this with the base station set up and double stub to assure horizontal accuracy. And once all these monuments are set, we come back and we run a solid bench run through there vertically, and we use a digital level, and we're adjusting out our elevations in between all of MnDOT's geodetic control. So we guarantee that this whole entire project has symmetry with its coordinates and elevations to assure every time the contractor's moving forward with their total station that everything is tight and we have no glitches. Next slide, please. Okay, the existing data. Now this is information that we as engineers, we're going to be designing off of. All these stringless milling projects, everything is truly based on existing information. So as of right now, we're seeing two types of data collection for our existing conditions, our ROADTOP elevations and horizontally where it's located. We have traditional cross sections that we're doing ourselves as surveyors. We'll go out, get our control established, and we'll come out and cross-section the project every 50 feet that we're using to establish our existing surface. This part, when we do our physical cross-sections, this is one thing that I got to be very adamant about making a point. If anybody's doing this traditionally, they need to be taking their cross-sections at actual even station and every plus 50. Just so when we start running our cross sections that it's real elevations and not interpolated elevations. So we're getting very tight accuracy, but we're having in between our plus 50 stations, we have interpolation. Now the big thing we're seeing right now that's been proven to be very, it's working very well is the mobile scanning with actually LiDAR data. You can see that we have very tight triangulation and it's picking up everything. And if we wanted to even cut, triangles or have vertices on wheel ruts, we could have them do that. The one issue though with the LiDAR data that we do have some fluctuations from 500th to 800th accuracy on the surface throughout the project. So sometimes you have to weigh that into your design, the accuracy. And the other existing data that we're dealing with is the actual in-place alignment. And this is another area that when we're dealing with existing conditions that we really need to take some time and verify that our existing alignments are truly following our scheme in the highway, where we run into issues down the road in construction. Flip to the next slide, please. Okay, here's a close-up of that same area we just had. And this is also right now on the active project on 23 in District 8. But you can see the southbound alignment over there at 1180. You can see how that alignment is following the triangulation very well. But then if you go over to the northbound alignment on the right, you can see there's a shift from where our triangulation is showing the crown of the road in our LiDAR in our alignment. Well, this is one of the things already in 2 times on this project that we had to go back and redesign all the models for Midstate and also for PCI for the concrete paving because of this shift in the alignment. So what's happening here, if we're not verifying up front that the alignment's following on the scheme or the crown of the road, we run our proposed templates on the alignment. So you start getting your pavement sections cantilevering over the PI. So it's very critical that in preservation projects, all of our existing data lines up. Go to the next slide, please. Okay, I'm going to really quick go into a broad overview and not get caught in the weeds with some of our design that we're doing on these roadway projects, these preservation projects. So basic information that we need that we already covered, the existing surface, existing alignment, the existing super elevation, if we're not going and introducing design standard super elevations and proposed super elevations, if we are going to be doing completely design standards, and some information from the owner, if it's MnDOT, a county, on the max mill depth. Typically, we see from GPR data. So next slide, please. Okay, here's the kind of the nuts and bolts of the Bentley software when we're starting to do design for variable depth milling, profile milling projects. So I don't have my pointer right here because I'm not in control, which I would be pointing things out. But what really is this? If you look up top, there is 3 separate templates that are ran against the baseline, which is our existing surface on the bottom. So what happens, and I'm just going to say the bottom one right now, is going to take the right edge of pavement and basically peg it on the existing surface. And then it runs across that template to verify that every other location, center line and pavement left, also is milling, because our goal is to have a minimum mill, and I'm just going to say from 0 to whatever it might be. Our goal is to have every part of the roadway milled. So we run that first template and we peg it on the right. If center line or pavement left does not meet that criteria and is floating in the air, it jumps to the next template. And that's going to drop it down on center line, and it's going to run it and verify that every location, pavement left and right and center line, is being milled. If not, it jumps to the third option. Eventually, one of these 3 scenarios will satisfy the criteria to say every location is being milled, and it drops a proposed template into our corridor at that location. So this completely goes through that process, the whole entire length of the project, and drops templates for our corridor that verifies that every location has a minimum mill. Then we go back and we run the same scenario, and we run it against a max mill. And this template right here is out of our Trunk Highway 63 project that we did down in District 6 for the first stringless milling pilot project a few years ago. So then this one we had specified 3.5-inch max mill. So then we ran that scenario, and eventually we have 2 separate corridors, one that is ran at min milling and the other that's ran at the maximum milling, and we generate surfaces off of these 2 corridors now. So can you jump to the next slide, please? Okay, so once we have, this is where I was going to do some live interaction with the microstation file, but I'm going to have to talk my way through it. Right now, we take this min surface and the maximum surface, and we import them into plan and profile. And we're looking at it in profile view. So flip to the next slide, please. Okay, so here's a close-up of that plan and profile, So if you notice that red line, that is our minimum mill surface that we establish off of running those templates on the existing. The blue line right now is the max mill. And in this particular, on this project, we had a 3.5-inch buffer that we had to design our profile to within this tolerance, or the best we could. And what we do, we first will take either the top or the bottom profile, and we will run a best fit profile and on one of them, and we will just change the delta elevation and raise it 1 inch. So we have a starting point, and now we have to start playing with all of our vertical curves that fall within that deviation. And sometimes that doesn't happen. And there's situations where when we import our surfaces, that these two lines will actually cross. My max mill and my min mill will eventually cross. And that's an area that defines or shows us that we have some issues right now with design supers and what's really out there. It's basically no solution worked. Anyway, flip to the next slide, please. Okay, so once we're done and we have this profile established, here's the actual typical. It was 5-inch concrete, and that's why the District 6 was so concerned about not getting carried away on the milling depths. So we basically took this lower template now and we ran it on that profile that we just set, falling in between our two min and max milling depths. Go to the next slide, please. Okay, here's just a plan view. This is our corridor of that same project. You can see two 12-foot lanes. This is basically after we developed our profile. We had our supers already keyed in, and we basically ran that typical section I just showed you. This is what our plan view of the corridor looks like. Flip to the next slide, please. Here's an isometric view of the same thing, so you can see the 5-inch concrete, the actual template drops that you can see out there. This particular project had bituminous shoulders, but we're really concerned about the template. And when we do our corridors and we work for concrete or like a PCI with concrete pavement and Midstate with the milling, we really are only dealing with one surface, and that's the concrete paving. The top of paving is the concrete paving that we would give a PCI roads or a stringless paver, those surfaces. But the bottom of concrete, that's our milling model. So when we're doing our corridors, that data is all being done at the same time. So flip to the next slide, please. So here's that exact same picture that I turned the template drop levels off, and you can see this is still there. These are levels that all of our corridors connecting every single template drop are 3D polylines. So our solid polylines on this that are not dashed, that's top of pavement, of concrete pavement. And the dashed lines are all bottom of pavement. So when we're dealing with surface models, it's very efficient once we develop our roads and build our corridors to kick out surface models. We just turn levels off and we make all of our surface models from 3D polylines. We don't use any spot elevations. So next slide, please. Okay, this is one thing I just really wanted to make a point out. This is back on the Trunk Highway 23 project out south of Grand Falls right now in District 8. The DOT out there did generate models for this project that could have been used by Midstate, PCI for paving. We went back on this particular project. We were hired by Dunnick to help out with all the modeling and supply models for all the contractors on this job. But you can see on the right was District 8's model that they basically drop templates every 25 feet through the whole entire project. And if you look at our surface on the right, the same area, we have a maximum 25-foot template drop but we also specify in open roads that anytime a horizontal or vertical curve exceeds 100 in a chord distance, to automatically drop template drops. So in areas where that's not a problem, it will start putting template drops every 25 feet, but in areas that needs more detail, it'll automatically put them in. It's a good way to get the quality that we need on the job for milling and paving profiles, but yet we don't get so big and go crazy where we're dropping templates every foot or 5 feet to try to make this model as detailed as possible. So that's part of the process too in generating models on a design side. You have to understand what the contractor needs and what they can use. Next slide, please. So once we're all done, with creating our corridors, what we do then is we will cut cross-section files through our entire corridor once we've got to the point where we've decided this is our final product. So we'll cut cross-sections, we'll label them, and this is something we'll print out, give to the owner if it's MnDOT, if it's counties or whoever's working for it, even the contractor. So we'll kick them out so they can review all of the rollovers and make sure everything looks right. Go to the next slide, please. And out of our cross-section files, we are able to extract information. So here you can see right now that over on the left, we have all of our stationing, we have existing, we have proposed, and we have all our mill depths. What you're not seeing on here that it somehow got cut off a little bit, or I'm not seeing it, we have also mile markers that like MnDOT materials, they can reference their information in their for their milling depths. And here you can see we highlighted anything that falls outside of our set parameters. And on this project, it was we wanted to verify that we were milling everywhere and a max of 3.5-inch mill. So this was a way we kicked out these spreadsheets and we identified areas where we did not fall in those parameters, and we allowed the owner to say, hey, is this going to be okay if we go 100 feet where we're a little bit shallow? And you can see over on the green right there, it's in parentheses, that's telling me that we have an area out on the edge of pavement that the mill popped out of the ground. So this is just a good way to review it and everybody knows what we're looking at. Next slide, please. Okay, once we're done, once we have approval from the owner that everything looks good, our corridors are done, it's just an easy export right out. And you can just see right here, right out of the Bentley product, we can kick out TTM files that go right into like Midstate's mill right now. They're running Trimble, so it's the TTM format. And one more slide, please. And our lines file, which would be two-dimensional lines, plan view that they're following, they're taking in DXF files. So it's simple import export right out, and that's it. So it's kind of a broad overview of some of the steps we do to get files prepped and out the door for our contractors that we work with. So any questions?
So Kyle, there's no questions in the question box, but one step that I recall is we actually were able to take your profiles and put them into ProVal to see how the final product rides.
Yep.
So that was something that I thought was just kind of mind-blowing, is we have a digital surface, and we will, if the contractor can in fact match that surface, certainly other things happen in the field, but you can actually know what the ride should be based on your model.
Yep, that is exactly right.
So with that, why don't we keep things moving and have Tom take control, or I guess he has control, but begin his presentation. Thanks, Kyle.
All right, just give me a minute to get my presentation fired up here. All right. Can you see that, Curt?
Yep, you're good to go.
All right. Well, thank you, everyone, for attending and taking time to listen to me for a little bit here. My name is Tom Abell. I'm the SciTech General Manager at SciTech Northland. We also work with Ziegler Cat, or the technology partner to Ziegler Cat. So you might hear those names, or I might slip in between both of them today, and that's okay. It's all coming through us. But wanted to spend a little bit of time after Kyle talked about the design to talk about the actual milling system, both the on machine and off machine, and in light of the topic of today, offer some best practices from our perspective as a dealer. So SciTech Northland is the Trimble dealer for Minnesota and most of Iowa, and we handle all the Trimble heavy civil construction equipment for that territory, milling, regular civil earth moving construction, and all the other fun stuff that Trimble has to offer. So I'm going to talk about kind of four big topics today. Just the automated machine guidance, or the 3D milling, stringless milling, whatever you want to call it. Go over that in regard from our perspective, and what does that look like. It's probably going to be a much simpler version of what Kyle just said, but I'm glad he went into the depth he did, because it truly is critical to have that design nailed down, right, to be able to do what we do. The machine's gonna mill what it's gonna, whatever we tell it to, but if the design's not right, then well, we're going to mill wrong. So, and I'm going to talk about the machine system itself. We've been working with Midstate and the Wirtgen mills for a long time, so most of it will be based around that. Talk about the off-machine components, the universal total stations, UTS, and what those are all about, and then just go over some results and through all that, sprinkle in some best practices for each piece. All right, so from our perspective as a dealer and a vendor of equipment, what does AMG, or automated machine guidance design milling, stringless milling, get us, right? Well, it's milling only what's needed, right? If we're doing the relative depth, you can see the pictures on the right-hand side. If we're going to mill 2 inches down, and there's those longitudinal ways in the road, well, we're going to repeat that as we place the mat back down over top. And if you think of that green line as the design, which is, again, the much simpler version of what Kyle just went through, if we can get that design to hit those predefined mins and maxes, and we can eventually get to the bottom picture there, where when we're milling, we're milling to the design, we can set the paver up for success by allowing them to have a much more consistent mat across the roadway. So what does that give us, as Curt mentioned, being able to throw those designs in the ProVal and see our theoretical ride, right? It gives us the opportunity to go after ride bonuses and increase smoothness for the paving after the pavers hit, right? Also cost control. Instead of filling in the highs and lows with extra material, right, we can reduce or control material usage and hit much more, or control how much we're putting down and make sure we know that when we're putting down a 4-inch lift, that it's truly a 4-inch lift. Right? And we can also simple and complex designs, right? Everything Kyle went through, those super elevations, and making sure that our design is right, to be able to handle that and build that before we ever get out to the field and start milling. One of the things that always stuck with me when we were talking about 3D milling was, even if we're running off string line or something else, right, we're still building a model. It's just they're doing it in the field, pounding hubs in the ground, running string line. So to be able to do that in the office and check it and verify it and make sure it's exactly what we want before we go out to the field and actually start tearing up material, I think is a huge advantage for us. Another way to look at that, this picture is a little bit more dramatic than the diagrams I was just showing, but you can see the highs and lows and what this looks like. It's tough to see on some of the pictures for the projects we've been working on when we're doing that, but I always like this picture to demonstrate what we can do. So switching to the machine system, like I said, we'll be focused mostly around the work and talking about how we're putting it on that, or what we put on it. And this is an aftermarket or shop, what we might call a shop installed or aftermarket solution. So we can take a mill out of the fleet or off the road today, put on a system and put it back out to work with the 3D milling, so it doesn't require any factory fit options. The architecture of the system looks like this, where we may have multiple mats on a working machine, but we're only running off one at a time. And those masts are talking back and forth with our total stations, using the total stations for positioning. The positioning runs back through our control box and sensors that we put on the machine to get mainfall and pitch and roll in those pieces, and our radio that's on the machine that's talking to the total stations over 2.4 gigahertz. And what we actually tap into is the Level Pro system in a Wirtgen, or if there's a MOBA system or a CAT grade system on a CAT mill, we're tapping into those 2D controls to move the legs of the mill up and down. So all we're really doing is providing positioning data to the machine, and then we're allowing the machine system, the 2D system and the system on the machine already to control itself from there. So on a Wirtgen in particular, this is a little bit more realistic what it looks like. We've got our radio and our power modules and our sensors mounted up as close to over the drum as we can get, because one of the keys to success here on a system like this is making sure our measure up is absolutely as tight as possible. We do most of the installation in a shop, or if we need to in a customer shop or in the field, but we do the final measure. We always do the final measure up when we bring it out to the job, get the teeth in the drum, and then do a final measure up to make sure we're measuring right down to the tips of those teeth right before they go into the ground. Like I was saying, this is just another way to think about it. We're providing the full 3D position relative to design, and then sending those to the 2D OEM control, and that's what's actually controlling machine hydraulics. Similar to what a contact sensor or sonic or something running on a string line would do as well. But instead of, like I said, running off the string line design, we're running off that digital model. And that brings us back to kind of the machine side of things, right? And I like this picture because it's the whole operation. In one picture, we've got the grade checker behind the mill. You can see off in the distance the total station, and that's where I'd like to go next, is to talk about the total station. As the system on the mill, you hopefully just saw it, it's fairly straightforward, and the total station setup is really the critical piece, as that's providing the positioning data of the machine. And here's another view of it from the other side. So literally switching our perspective here to the UTS, the off machine. So we run a couple components there. It's a Trimble SPS 930 total station, and then we've got a survey instrument running, an MT900, or excuse me, MT1000, or an AT360 machine target for the grade, or off machine target for the grade checker. And this is where we get into Curt's frickin' laser beams, as he said, that's where the total station is bouncing back and forth, or not exactly, but electromagnetic radiation to be sure. Bouncing that signal back and forth between the machine target or the grade checking instrument. Okay. So the SPS 930, there's just some facts about what it does, right? As a dealer, I feel compelled always to throw up some of the marketing pieces to make sure that you guys know we're talking about best practices as well. We want to make sure we have the best equipment out there. And the 930 is certainly, that's our fastest gun. It's a 1-1 gun or 1-second gun. But to get to sort of best practices on a milling job, the total station is so important, and not only how it relates to design, but when you're shooting in control, right? I'll say it, I think 3 times here in this presentation, but the control on any milling project can't be tight enough. That's where it all starts. So we always want to make sure that our total stations, when we're resecting in on, we always try and do 3 or 4 control points as a best practice, and we know exactly where our total stations are, and we can capture any back control that we may see. But making sure we're resecting correctly, we're doing the right, we're shooting enough control to make sure we know exactly where that total station is. So when we end up pointing at the machine, there's not any concern about accuracy issues. We're chasing millimeters here, so it's a big machine. It's really important to be able to do this. It runs the machine and the survey instrument. So typically on a job, and I know Dan's going to talk about this a little bit more, we recommend 5 total stations, and Dan will hopefully back me up on that, because it's a matter of production, right? If you got 4 running the machine, you always want 1 behind the machine checking grade to make sure the mill's doing what it's supposed to be doing. It's a trust but verify situation, and we don't want the mill, if there was a mistake made in the measure up and that final measure up in the field, we want to catch that as soon as possible, or if something is wrong with the design, or there was a disconnect between the design that's going in the machine versus the design that's in the survey instrument, then we want to catch it as soon as possible. All these tools are great, and the laser beams are great, but they are still tools, and they can only, the garbage in, garbage out situation, just like most of the equipment we sell. So if we've set up our total station correctly, it moves into management of those total stations on the machine, right? We have the grade checker behind it, but then on the machine side, the benefit of the Trimble system is we can do multiple total stations tracking the machine target at the same time, which is certainly a best practice. We want 2 or 3 total stations tracking, so as the mill runs down the road, it's able to switch seamlessly from one to the other to the next, and then the survey techs on site can move total stations that have fallen behind the machine back up in front to catch the machine again and allow it to keep working and running down the road. So this is just a little bit of what our system looks like, where we can track multiple targets. This is in meters, but we can certainly change it to feet, where you can tell where you are, what's the next total station instrument coming up that is tracking, and then as the operators get close, they're able to promote and switch using the buttons on the right there, promote and switch to the next total station. And to the machine, it's seamless. There's no stopping. There's no waiting for it to connect. It's you promote to the next total station, and if there happens to be a little bit of maybe a bust in how the elevation or how one was backsided from one of the other, the system's smart enough to capture that and zero it out when you're switching from total station to the total station. So a lot of this gets to kind of the bigger picture of the whole site and how a contractor is managing it, and total stations where they're set up is critical, and it's a lot about how the whole crew, both the DOT, the owners, the survey firm, whoever's moving the total stations around on site, they're all talking together, and everybody kind of knows the plan. Where they set control, as Kyle said, every 250 feet on either side of the road, that's critical to be able to manage these total stations as the mill runs down the road. A few more tips, right? Is with that in mind, having a milling plan and making sure everybody's talking is critical. That if nobody's talking, if the mill operator thinks they're doing one thing and the survey, the person moving the total stations down the road thinks they're doing another, it can cause a lot of problems. But I think what we've seen with Midstate, WSB, and MnDOT is everybody's talking, everybody's communicating, and it's certainly a key to success and can keep the mill running down the road. And with that, having total stations to match your production goals is also critical, whether it's 3 or 4 or 5 or 7 or 10. How fast that mill needs to run down the road is something you need to talk with your vendor with, and make sure you've got enough equipment to make sure that you're milling at the production you want. On the total station side, we always want to try and limit shots to 500 feet, unless it's up to 650, but 500 is really probably where we want to limit the top, and that's kind of the top end of a shot. So where we're putting our total station, we never want to be more than 500 feet away from the machine on either side of the machine when it's running. If they're milling over hot surfaces, a hot day, sometimes it does even get hot in Minnesota, but if it's a hot day or that somebody's putting down material on a different part of the project and we've got hot asphalt out there, making sure we're not shooting over hot surfaces is something we always consider, and make sure we're not getting refraction as the total station is controlling the machine or the survey instrument. Overall, like I said, you're hunting millimeters with a 40-ton machine. So a few things that we can do. The system's going to do what it's going to do. If it's measured up right, it's going to mill to the design. But control is critical. I've been on projects where control was set with GPS and not, it wasn't a level line loop ran through it, and somebody didn't put a total station on it after they set up GPS. They maybe set it in some poor signal spots under power lines, things you normally want to avoid when you're setting control, and it really affected the performance of the system. And I can't stress that enough, that control is critical. It's where it all starts, right? If there's error there, everything just compounds after that. UTS calibration, the actual equipment, right? We want to make sure our equipment's good, both on the machine. We measure the machine up one last time when it's on site and we get the teeth in, right? So we want to make sure our total stations are calibrated before any mill job. and making sure they're running well and are tight, because again, it's any source for error when we're milling as accurately as we can, we want to eliminate. And grade check, right? You want to be grade checking in millimeters, you want it to be tight, and part of that is why the pictures on the right are there. It is making sure even the simple things like a worn down tip on a grade rod is checked at the start of the job. That can be when you're measuring in millimeters, when you're measuring that tight, a worn tip can be the cause of an error and cause of problems on site. So making sure all our tools are tight, not just the big things like total stations and the machine, but the little things like grade rods and tips and all those fun little pieces you tend to forget about. And what does that all build towards, or what does it get us? Well, with Midstate and on the projects they're on, I just did a quick shot of some of the data that we can report back wirelessly. So all the data on the jobs we've worked with them on have been sent back through VisionLink and then captured that way. Nothing's pulled off the display. It's all sent over the air back to VisionLink. And this is just a snapshot of the raw data. Nothing's been cleaned up. Nothing. It's what we recorded on site. So I'm zoomed in a little bit closer here, but if I scan the other parts, say, yeah, we've got some spots where you can see the mill pulling out, and for the most part, it's stuck to high. But when we're doing, I think this was I-90, this might have been 23. I pulled this from quick, but when we're doing that much road, we're doing miles and miles and miles of road, and we're hitting over 99%, 99.9 under 200s, right? It's pretty impressive. And I've always been sort of astonished by the results of these projects as they come out. So it's been fun to see and fun to partner with. And, when you put it all together and you get everybody together as a team and we're all working together, WSB, MnDOT, and Midstate, we can get some pretty cool results. And this is a picture from the actual project. It was early on when we first put the mill on ground. That's why there's a bunch of people standing around, but it's been very neat to see, and why I love what I do is when we start getting those laser beams pointed at machines and are able to control it the way we can, it's a lot of fun. And that's pretty much everything I have. So I wanted to end and say thank you. And like I said, it does take a team, and I love this picture because it's got everybody in it from that first project we were on down on I-90 and MnDOT, WSB, Ziegler folks, SciTech folks. We're all there together. And if there's any questions, happy to answer.
The one question did come in, but then I think you answered it, but it's, it might be one for you or it might be one for Dan. Anytime we're talking milling and we're talking millimeters, you've got teeth wear. And I think Dan might cover that in his presentation, but we're out there measuring in millimeters and we know those teeth wear down. I don't know if that's something you want to comment on, Tom, or Dan's going to take that.
Yeah, it's certainly a factor. I say, why don't we see if Dan touches on it, otherwise I can certainly kind of chime in at the end.
All right.
Dan doesn't.
Why don't we wait for the end? Why don't you go ahead and take control?
I believe we're up and running here. So yeah, my name is Dan Schellhammer. I'm the Vice President of Midstate Reclamation and Trucking. Our group, we focus on asphalt recycling and have ever since our business started back in 1984. And we've always prided ourselves on incorporating technology into all the different disciplines and things that we do. So with that, a lot of things I'm going to say, I'm going to echo what both Kyle and Tom have already said, but just going to have a contractor's perspective and a contractor's spin on our experience with 3D. So, hold on one second here. No, I think I'm going. All right. You guys see my screen okay or not?
Yep,
It looks
we got
good
it.
now. It
Okay.
well, now it flipped back.
There
Good
we go.
now.
All right. So, yeah, the things I want to cover today are to start out, just talk about how we as a business and as a company ramped up into this technology and implemented it successfully. Want to share some lessons learned from our perspective. Definitely want to highlight the technology's capability for real-time verification, and then just kind of round things out with how we're using the technology and some help that the industry, the 3D milling and paving industry needs from owners. So as we ramped up and got ourselves involved in 3D milling, the first step in that process for us was selecting a vendor. And we definitely kicked the tires on several vendors throughout the industry that provide 3D milling options. Really the pricing was really competitive amongst everybody, but we ended up going with Trimble because of the local support that they vouched to give us, and the training and the way they were able to back us up and get us up to speed really quickly. And that was just a huge value add. So when we were selecting which company to go with, Trimble definitely had with Tom and his team there at SciTech. They had the best proposal and were willing to really help us out. So that's really important when you want to implement a new technology, is to bring in subject matter experts that can help you become a subject matter expert yourself. The next thing we need to do is we need to communicate the value of the technology to our team. All right, so we have crews of milling operators that once they hear things, about 3D milling, they're worried about, well, is this technology going to take my job away, right? And we really need to talk to them about, it won't take your job away, but it'll be able to enhance what we do. You'll be able to do what you do better and faster. And it'll help us as a team get more work and be more productive. So that was also a key component to us implementing this work here in this service line at our business. And then next step was identifying a technology champion. Like any type of implementation process, you have to have a champion for that process that carries things through, that does really the hard research and just grinds. And that person for us is Brian Hill. Brian has been in and around the construction industry for many years, but I think as recently as probably 3-4 years ago, had little to no survey experience. But Brian really took to the technology and the training that SciTech was able to supply to us, and really helped mold the way we do things. And so if it weren't for that technology champion, we would not have the success that we have had milling in 3D. And then training. So our entire team, whether it was managers, estimators, AMG technicians, or operators, they all went through training both in the classroom and out in the field to learn about the process, the equipment, what it was capable of, what it was not capable of, what its limitations were. And that was very instrumental in implementing 3D milling for our company. And then doing a small field test before we actually got out on the interstate with MnDOT was a key step in us ramping up to just vet out the equipment and work with it, learn about it, and know what we were doing before we got out in the grade. All right, so some of our lessons learned. Really the things start and end with 3D milling with having tight tolerances. All right, when I talk about tight tolerances, that is the depths and the cross slopes that we actually mill versus what the model was that was produced by an engineer. And so that process starts with retrofitting our equipment. We run Wirtgen mills with Trimble's equipment. All right, so that equipment doesn't come from Wirtgen ready to 3D mill. We needed to retrofit and add this equipment on. And Tom talked about just how important that fit up is of that equipment. You can be off and not even know it if you're not properly bolted on and calibrated. All right, so and we always want to, like Tom mentioned, you get that equipment initially set up in a shop, right, in a controlled situation, and then you need to go out once you get in the field. You have to recalibrate that equipment to know right where everything's at. So heard Tom mention trust but verify. I smiled when he did because that's something that we do all the time with 3D milling. We trust the technology is going to work, but we're constantly verifying that we're on the right path. Lesson learned on, the first project we did with MnDOT was on I-90. It was down near Fairmont, Minnesota. And it was a project that had an old concrete panels on it, had been overlaid with asphalt. And the plan was to then 3D mill some of that asphalt off and put a concrete overlay on top of it. We ran through and we did the main line first with really no issues. And then we went to the off and on ramps. And the way that the models were built for that project, the main line was modeled, and then the on and off ramps were modeled separately. And where those two met, the grades were off, and the elevations were off, and the cross slope was off, and they weren't tied in properly. So with our first experience there, we learned that one of the key things to do is, as you're mating up models next to each other, whether it's a continuation or you're going off on another roadway, you really need to make sure that those elevations and grades are tied together at the tie-in points. So in case in point, you don't want to have your grout lines not line up there. Another lesson learned, this is going to sound like a broken record, but really in order to be accurate, you have to have accurate control. And in order to have accurate control, you need to give survey teams the time that they need to establish those and invest in accurate control. If you don't, I would say this is not a lesson that we learned, but after we talked to industry partners at NRRA and talked to folks at Trimble and some folks who do a lot of 3D milling down in Iowa, it was clear that having accurate control was probably the #1 way that things get off. All right, so it wasn't a lesson we had to learn, but it was one that we, I guess, learned through education. But really need to communicate and emphasize the need for those control points to the entire team. So that's working with, for us, MnDOT, the designer, the prime contractor, and everyone throughout the project team of how important that is. You need to be aware of seasonal changes that can throw off your control points, right? So especially up here in northern climate in Minnesota, if we were to take control and have that all set up in the fall and expect those control points to make it through the winter, through the spring, and then be right where they're supposed to be, that's just not going to work out. All right. So whenever possible, you want to use the same control points when you're collecting the data for creating the surface model for when you perform the automated machine guidance work. So, and again, Tom, I'm going to back Tom up on this about some of our lessons learned here, but with the total station spacing, the number needed, the number of technicians. So for us, in order to maintain that accuracy, we kept our total station spacing at 500 feet. So the furthest away we got from a total station on our projects is 250 feet, right before it transfers itself up to the closer total station. And we really found that that's what we needed to ensure we were accurate, also keeping those total stations that close. If there was an issue with a truck getting in the way or something else, we could gather that information from a different, closer total station, which helped keep our production up. And speaking of production, I would agree with Tom, where if you want to be able to mill productively with high productions in this type of mainline environment work, you do need 5 total stations on a project. You need those total stations so that you don't get backup for the trucks, so that your technician has time to leapfrog those total stations. And you also have time for a second technician to ensure that they're verifying our milling depths. And so do need 2 technicians on a job. Each of them is going to kind of have a different job assignment. One of the technicians will be behind the mill, verifying our milling depths at all times. And the second technician is going to be leapfrogging our total stations on down the grade as we're working, and also probably doing some administrative work and maybe some computer work when they have some free time. But there's really, when we're really getting after the square yards and getting after things, there's really not a whole lot of extra time for either of those people on a job. So I talked about that job near Fairmont, Minnesota on I-90. We did that job, the first phase of it last year in 2019. There was a lesson that we learned there. I did mention that that job was, it was an existing concrete road that had been overlaid with asphalt. The plan was to remove a portion of that asphalt and put a concrete overlay on top of it. With the first phase on westbound, we had a predetermined asphalt milling depth, was set and went through and milled the job. And there were some areas where maybe an inch or less asphalt remained on top of that concrete surface. And with construction traffic over time and those heavy loads, it beat up that last remaining sliver of asphalt on top of the concrete. And we ended up having to do some leveling course just to get things back to plan to make things work. So that added an additional cost. So on the second phase of that project, we brought the model elevation up slightly and no leveling course was required. So lesson learned would be to really pay attention and verify your existing asphalt depths on a concrete overlay project and get that incorporated into your design so you don't end up having to do a leveling course on a job. Another job we did with MnDOT was Trunk Highway 23 near Granite Falls, Minnesota. And this project was very different than I-90. It was a trunk highway in MnDOT's trunk highway system. So there's lots of curves and turns and super elevations and grade changes. So it was much more dynamic job with as far as the profile goes. And what we learned there was just getting out on that job and with the intentions of being able to move through things as quickly with the same amount of prep is not realistic when you compare it to just doing a straight interstate mainline job. What you need to do is you need to give your milling team and your technician just some time to work through your milling plan, right? And talk to each other about which areas will be more sensitive and more difficult to mill in 3D and have them just kind of work through those processes and get them a little extra time to review models. Would definitely be a lesson learned when it comes to that. Definitely want to highlight the real-time verification that MnDOT's requiring per their specification. I know MnDOT's a great partner in that when they're putting together a specification, they work with industry to see what industry is capable of, and they incorporate that into the contracts that they then let. And having that interaction with folks like Curt or with Rebecca Embacher, it's a great way to partner and really maximize the potential of technology. And it's been a great experience doing that with the Trimble group, led by Tom and by guys, like Kyle when it comes to design. So, but on these projects, the AMG technician followed behind the mill to verify the depths that we were cutting, right? Were we cutting to the planned elevation, the modeled elevation? And that information was transmitted up to the cloud, and in real time, anywhere in the world with an internet connection, you could see how accurate we were throughout the course of the day in real time. And so, I know we viewed that information here at Lakeville at our office. I know MnDOT reviewed that information remotely as the work was going on. So it was a really great step forward and a great indication of what's to come with just 3D technology and how it's going to become more user-friendly for everybody. Lesson learned, whenever there's an option for a larger display or better display for your technician, it's money well spent getting that. It makes them more efficient, and it's just a better way to go. And I think the question might be a good time to talk about milling teeth wear versus the depth of our cut. So as those teeth wear down, that technician behind the machine is keeping an eye on our tolerances, and we're making slight adjustments as those milling teeth wear down into the computer, the PCS 900, to ensure that we are shooting the modeled depth there. So that all kind of happens with that technician running exclusively behind that machine, making those slight adjustments as we work our way on down the grade. So some highlights of the technology: quantity control on projects. We're able to determine ahead of time just how many cubic yards of asphalt need to be removed on a job. And that really helps a contractor tighten up their bid because they know just how many trucks they'll need. They'll know how much time it'll take. And you'll see a more aggressive pricing, I guess, for those removals from contractors, and then vice versa, when you're bringing the material back in, whether it be concrete or asphalt, you won't have such large swings in quantities, right? So you should have very accurate quantity control for those materials that you're importing back to the job. We talked about the ride improvements you'll see with ProVal. You can know ahead of time if the job is milled correctly, just where you'll end up at. And that's a great savings and a great tool. And then also you'll be able to truly do variable depth milling with 3D, right? You're not basing on the sensor length of a milling machine, right? You can carry out that horizontal line, excuse me, indefinitely if you want to, and then just, mill yourself veritably. For us as a contractor, some growth areas that we're seeing outside of DOT work and county work in the private sector is on parking lots. So we're able to go out and shoot existing parking lots. It could be small or very large, and make drainage corrections with our milling process. We're also able to accelerate construction because we're able to do very accurate removals. So say you had a FedEx terminal that was going to shut down just for 36 hours to do the whole entire parking lot. In the past, contractors have had to have aggregate on standby if they did too much removal, or additional trucks to take additional material out if they didn't get enough material out. By being able to mill in 3D, you can get right down to the exact elevation that's planned by the engineer. And then moving forward to next steps, the technology for integration of 3D. We do need some help. The industry does. The help that we need is with designs for one, to definitely consider moving towards creating all designs in 3D, so that, if you're not going to mill in 3D today, if you're going to go back and do a reconstruct 10 years from now, you still have the 3D model established. I just think moving towards creating models in 3D is a good best practice. And then a question that we get a lot from folks now as we're working ourselves into this technology is total AMG control possible? Yes, it is what we're hearing from the vendors. But when you move from, a human controlling a mill or a different piece of equipment to technology controlling that equipment, really there's no legislation that says who bears the responsibility and liability if that technology fails. And that is something that as an industry would help accelerate its implementation if I guess politicians or some other folks could figure out where that liability might land. I guess as an industry, we don't have a strong stance on where the liability should land. It just, whoever gets it's going to need to account for that in the way that they price and do their work. So with that, that kind of concludes what I had to say about frickin' laser beams. And I don't know if there's any questions out there remaining or not.
Okay, we didn't coordinate that.
I dropped that in last second.
Well done. So the first question I had is, someone said they wanted to see my dog again. So there she is. Since I'm Dr. Evil, and Dr. Evil usually had a white cat on his lap, this is the best I can do. Actually, we got a few questions here. The one is the tolerance between the model and the milling machine. And I think we all know that one. Should go ahead and tell us what you were able to achieve out there, Dan.
Yeah, I mean, our tolerance, it was, almost 100%, 99.9% of the time, we were within a couple hundredths, even down to 100th. And I know from the contract that was let in 19, going in, that was I-90, going from there to the contract that was let on 2020, the specification even changed slightly on how we collect that data. Wanted to collect more of it, and we were required to be even more accurate.
Yeah, that's where 0.02 is. We didn't think we could do it, and now it's like, well, this is nothing.
Yes, it's not nothing. It took a lot of effort by lots of folks, but everybody involved was instrumental in making that happen.
When you're successful 99% of the times, from my point of view, it looks like that was easy. But that's just where I sit with my dog on my lap. Question about, and I'll handle this one. So we did the proval of the model originally, the surface, to see what it would look like, and actually we're able to find a few things that the automated system didn't quite find. If I recall Jim Schneider telling me the model run through proval, the IRI was under 20, which I was pretty excited about. So then you get into reality. Certainly the milled surface, you're over a jointed concrete pavement, and some of those joints will shell them out, or it's not necessarily that solid. I know I was on that surface on I-90 and I drove it at a speed that may or may not have exceeded the speed limit, and it rode really well until you found those little areas. We did try and measure the IRI down there. I hate to say a number because I don't have it in front of me, but it was certainly not that smooth, but it was smooth enough to be in a very good condition in terms of if we just turned the pavement loose to people, with the exception of those areas that shelled out. And ultimately, when the concrete is paved on top, then you have, certainly consistency of the mix that impacts the ride. We had some issues with the ditches not being terribly stable, so the tracks for the concrete paver were sometimes sinking and coming and going. So we did not pave it at under 20, but this was one of the better riding jobs for that particular concrete paving company. So the model says you can get under 20, but reality is something a little different. But in the end, we did get a very good project. We answered the question about the tolerance. Someone's asking a question in terms of the agency's consideration for this, and is it a worthwhile investment? Historically, for an unbonded concrete overlay, we've just corrected everything with concrete. So if we had a super or something cross slope that wasn't quite right, we just made the concrete thicker. And that is pretty expensive and kind of wasteful, getting 12, 13 inches of concrete on the high side of a super. Your baskets aren't in the right place anymore. And it's, when you have the ability to do this kind of stuff and you can save that amount of material, it just made sense for us to do this. We are looking at being a lot more efficient with the amount of material, being a lot more efficient with how we measure and pay for the material, because everything is so much more uniform. And when you are in the pavement business, uniformity is kind of everything. So it's not really a question of how bad is the existing surface. It's more a question of how good do you want your pavement to be when you put it on top. And as was mentioned, the projects we've been doing have been concrete overlays on something that has at least some asphalt there. And there's one question about whether the presentations will be available for the future. And I assume that Lauren will say yes, and eventually I'll turn it over to her. And I just again want to thank Kyle and Tom and Dan for putting all the hard work into putting this presentation together, so that there's a lot of lessons learned, and we expect a few hiccups here and there, including hiccups with the technology on the presentations. I'd say everybody give them a round of applause, but that doesn't work virtually. Again, thanks everybody for your participation. And again, Lauren, do you have any wrap up, including where they may find these presentations?
Yeah, thank you. I will be posting the recording onto our YouTube channel, the National Road Research Alliance YouTube channel. We'll have this hopefully by the end of the week. And then if you each want to send me your presentation slides, I could also post PDFs of those to the Pavement Workshop webpage as well on the NRRA website.
Okay, again, thanks everybody, and we are using frickin' laser beams to build roads.